As an announcement, on Sunday we're going to be doing some kinetics calculations, and you're welcome to bring your computers, but it's not required. I'm going to be recording the lecture like I always do, so I'll be using Excel, and so you can either do the in-class exercise using Excel while I'm also doing the example, or you can just watch. So it's truly optional for you to bring the computer on Sunday, depending on how you learn best. Homework number 2 is due on Tuesday of next week, and as a reminder of my office hours, they're Sunday, Tuesday, and Thursday from 10 until noon. And if you need to meet me during other times, it's best to fix an appointment with me so that I'm certain to be in when you need to come see me. Go. Yeah. Excuse me? If you're wondering why I'm putting L on the papers, it's so that I can keep track of who's on time to class. There you go. Okay, so we're going to continue talking about materials balance today, and then we're going to begin on kinetics. So any questions about these announcements? All right, we're going to begin with the in-class exercise that I've just given you. And it starts off with you doing a little bit of research on a technology that's called activated carbon. And do you remember we talked about the algae in the river during our first class period? And then on the homework 1, I asked you to find out about a chemical. And it turns out that that chemical, many of you identified the fact that that chemical was accidentally discharged into a river last January. And so it polluted the river water that the drinking water is supposed to come from. And so activated carbon can be used for treating water that's had algae in it that's released toxins, or it can be used for treating chemicals that spill into the water. So it's very useful. So what I'm going to ask you to do is you can work together in pairs or in a group of 3. And in problem 1, just do a quick research on the internet using your phone. And so even if you're just looking at Wikipedia, that's okay. Find some basic beginning information about activated carbon. And then part 2 of it is trying to solve some mass balance calculations. And I'm not going to give you too many hints to begin with because I want to see what you can kind of figure out on your own, but I'll be circulating around with the answer to problem 2, and so you can check to see if you've gotten it right. All right, so I'm going to pause the recording, and the time is yours to start working on in-class exercise 3. As a reminder, so in the first step what we did was we found out how quickly is the pollution entering the filter. And so we found the mass flow rate of the pollution. If you multiply the volumetric flow rate, Q, converting it to cubic meters per second, because there's 1,000 liters in a cubic meter. So the volumetric flow rate is 0.025 cubic meters per second. Multiply that by the concentration of pollutant, which is 3.4 grams per cubic meter. So our mass flow rate is 0.085 grams per second. So that's how quickly the pollution is entering the filter. And so what we want to know is how quickly is that filter going to fill up with pollution. What you learned about when you were doing your research is that this process is called adsorption. And the high surface area of the carbon, combined with the fact that the carbon is highly attracted to other carbon molecules, like carbon that's inside of the pollutant, they attract together and the chemical gets stuck on the surface of the carbon. So in the second stage of this problem, how much pollution in grams can the filter hold? And what we know is in total, between the 3 filters, there's 5,400 kilograms of carbon. Okay? And then we have a ratio of 0.15, which says for every kilogram of carbon, it can hold 0.15 kilograms of pollution. So that tells us when this is full, that 5,400 kilograms of carbon will have removed 810 kilograms of pollution. So do you have any questions so far? And remember, if you have a question, chances are several other people do also. So I welcome your questions. I like it when students participate and voice their uncertainties, because that gives me a chance to help explain. Okay, so then the final thing, you know how quickly the pollution is coming in. You know the total amount it can hold. And so this last thing, it says how many days until the carbon needs to be regenerated or replaced. So you can just look at the units. If we have grams per second and kilograms, and that tells you what to do. Change it from kilograms to grams, divide by the mass flow rate, and it tells us in the end we have 110.3 days, and then the pollutant will have filled up the capacity of the activated carbon to absorb it. Okay, so any questions about this in-class exercise? That's a good question. Actually, it's just like if you had sand and you're shoveling sand into the tank, and so the activated carbon is like crushed up coal, or sometimes they use coconuts. For some reason, I don't know why, but if you burn coconuts, that turns into a really nice activated carbon, just the outside shell. And so they crush it up, powder it, and so it's full to the very top with the activated carbon. And after 110 days, if we don't replace it, then the pollution will just go through. The activated carbon will have no effect. All right. So remember, before you leave, be sure and put the in-class exercise here so that I can give you the points. At the end of class, not right now. Are there other questions before we move on from the example? Now, what we've been doing so far before today was we were looking at mass balance in terms of what if there's no reaction happening. Steady state, meaning that conditions don't change over time. The flow rate is the same in 1 hour as it is right now. That's what steady state means. And until now, we've also assumed that there was no chemical reaction. That's not always true. Sometimes there will be a chemical reaction, and so we need to expand our understanding of mass balance to include what happens when there is a chemical reaction or bacterial growth. And so let's look at that same box where there's a flow in and there's a flow out, and talk about the rate of a reaction going on inside of this container. And so there is the idea of mass flow rate. The change of mass inside of this tank over time depends on the flow in and the flow out, which we've already seen. But what we're going to talk about today and moving forward is what if there's a reaction? That's what R stands for. It stands for reaction. It could be a chemical reaction or a biological reaction. So if you know the rate constant and multiply that by the volume of the reactor, then that tells you how quickly the reactor is having growth or consumption. Sometimes reactions will reduce the concentration of a pollutant, for example, and so that would be consumption. Or if it's bacteria growing inside of a tank, then something would be produced. The bacterial cells would be growing and produced. And we'll talk about both of those over the coming days. And so R is very important. How quickly is the reaction happening? Some reactions are fast, some reactions are slow, and we're going to be talking all about reaction rates today. So a reaction rate just tells you how quickly the mass or the volume of some material is changing over time. And if you look, R is defined as the change in amount with respect to time. So dA dt. It's the change of mass or the change of volume over time. There's three kinds of reactions we'll talk about: zero order, first order, and second order. And I'll explain on the coming slides what each of those means. So first of all, a zero order reaction means that the reaction rate is steady and it doesn't change depending on how much there is of something. Some reactions actually slow down or speed up. But a zero order reaction, it's always the same rate. It's like if you're driving in your car at 100 kilometers per hour, you're not speeding up, you're not slowing down. A zero order reaction means the speed of the reaction is steady. And so K means it's a constant. R is the rate of the reaction rate is constant. That's what R equals K. If I, in a quiz or something, if I say, explain this, and you would write, the reaction rate is constant. That's the English interpretation of those symbols. So the change of mass A over time is constant. dA dt means the rate of that change is constant. So here's a graph. It's showing it's steady. It's always increasing the same amount. Rise over run is the slope of the line. Everybody here knows how to find the slope of the line, right? Delta amount divided by delta time would tell us the slope. And that slope is straight. So that's zero order kinetics. It's very simple to find out the concentration at some time. Like, what's the concentration at time 4? Well, it's the starting concentration plus whatever the change is. And so if we knew the slope of this line, you could say the amount at time 4 is the starting amount plus the slope times the time. And then you could find out the concentration at any time in that way. And so one example of a zero order reaction is when inside of a tank the water has sediment, and the sediment is settling out. And here's a picture of some UV tubes that are used to kill bacteria. And these tubes wouldn't be very good because they're coated with material, and so the light can't shine through them. And UV, not only does UV cause skin cancer, but also UV can kill bacteria. And so sometimes they'll shine a UV light into drinking water as a way of killing the bacteria. But it doesn't work if it's coated with the material. So one example of a zero order reaction is how quickly that coating gets on the outside. So you can predict when the tube will be covered in the coating just by using this zero order kinetics. Now a first order reaction is a little bit different. The easiest way to show it is the graph. It's not a straight line anymore. In the previous slide it was a straight line. So why do you think in this curve, the first one on the left, it's pretty steep to begin with, but then it's getting less steep? What's like the physical interpretation of what's happening to the reaction rate over time for this one? It's decreasing. Yeah, it's slowing down. And so at first, whatever this is, we don't know what it is. It's the amount of something. There used to be a lot of it, and it was declining very fast. But then as time goes on, as the amount gets lower, then the speed of the decrease slows down as well. And let me give you an analogy. When everyone is sitting around the table at dinner, and there's lots of food, it's piles of food, people eat very, very quickly, right? But then when there's only a few things left, people get a little bit more hesitant. Nobody wants to take the last bit of food because then it looks like they're taking too much, right? So people are slowing down. As the amount decreases, it slows down how quickly people eat. And so here, what you should write on your paper on the side, you know, in this space that I give you on the side, for a first order reaction, the rate of the reaction depends on how much there is. And that's what this says here. The change of the component is proportional to the amount of the component present. So maybe in simpler language, just to keep it in your mind more easily, for the graph on the left, you could say lots of component equals fast reaction. Little component equals slow reaction. So how much there is dictates the rate of the reaction. So now look at this. R, the reaction rate depends on a constant multiplied by the amount. That's how you can tell how quickly the reaction happens. So that's first order kinetics. So this is a consumption reaction, and this is a production reaction on the right. The amount is increasing, something is being produced. The amount is decreasing, then something is being consumed. So this is like a big, complicated idea at first. It can be a little bit confusing. So what questions do you have about first order kinetics so far? Nothing pops into your mind yet. Okay, if you have questions, let me know. So let me do an example very briefly using Excel. You're going to do some more of this when you are in class on Saturday. So if you bring your computer and it has Excel, the in-class exercise will ask you to do something similar. So here we have a table of data. We have, at a certain time, the amount of something that's present. So let me copy this data. I'm right now right-click, copy, and then I'll move to Excel and paste. Okay, so let me insert the row there. So this is time, and this is amount. What we want to do is we want to see, is this zero order kinetics or is it first order kinetics? And so I'm going to insert a chart, and I'm going to select the data here. For the x-axis I want time, and for the y-axis I want the amount. If it's zero order kinetics, what should it look like? It should be linear, right. So I'm going to say zero order, and I'm going to have a question mark here, like I'm checking to see, is it zero order? It doesn't look like it's zero order kinetics. Okay, and one way to prove it to myself is I'm going to right-click here, and I'm going to add a trend line, a linear trend line, and I'll have it turn on the r squared in the equation. If I try and fit that data with a linear trend line, it doesn't fit very nicely. Okay? Okay, so I'm going to copy that, and I'm going to check with first order kinetics by doing this. This is the magic right here, ln of the amount. And so I'm going to do equals ln, that's the function for logarithm. I want to take the logarithm of this amount, and then I'm going to drag this formula down like that. Okay, now I'm going to copy, Control-C, and then Control-V for paste, and I'm going to rename this one, is it first order? Okay, and when I click here, it's showing me these are the two things that are graphed. I'm going to drag this blue one over, and then it changes it to a graph of the logarithm of the amount. And suddenly, it's linear. And so that tells me if you take the logarithm of the amount and you get a linear trend like this, then this is first order kinetics. And so K is the slope of the line in this instance. So K is 0.25. So this is a very useful technique in order to find out if, when I say characterize the kinetics, that means find the slope of the line and find out, is it first order, zero order, second order. So the answer, first order, exclamation point, because it is. It's no longer a question, is it first order? And so it's always a good habit to add the titles here. So let me do axis titles here. This one was time. Was it hours? Hours, yep, hours. And then over here was the logarithm of the amount. ln of amount. All right. So that's the first demonstration you're going to get on kinetics. Okay? Any questions? Yeah. Oh, so what's that? Yeah. So you're saying, what if we did a trend line, like one of these? Well, I don't think that would work. We can try. Let's see, logarithm. Let me delete this trend line and let's put in a new one. Okay, so that's a good question because it gives you those options. Okay, so if we do logarithmic, it's not doing a logarithmic trend. Let's see, logarithmic. Yeah, it won't work. It's because if you look at the shape that it's suggesting, add trend line. Here's the shapes that it's suggesting. It's suggesting there might be exponential, linear, logarithmic. It's expecting it to be fast at first and then slower at the end. And we've sort of got the reverse of that. We've got it slow to begin and then it's faster at the end.
So it must be exponential.
Well, exponential, yeah. The problem with that is it doesn't fit what we know about. You get a good R squared, but there's no slope that we're going to be able to use in the formulas that we'll need later on. So the method that you should use is take the logarithm of the data. Now, this is the only approach that can work in a regular way. All right. So once you take the logarithm of it and you get a formula, the slope of that line is your rate constant K. A second order reaction is similar. The rate of the reaction is K, which is the constant that you'll find, times the amount squared. So you can find out how quickly the amount is changing. And so a similar approach to what we just did, if you find the time and you have amounts, then it wouldn't work for what we just did. Like what we just did, we had time on the x-axis, and on the y-axis is the logarithm of the amount. So what you need to do is actually 1 divided by the amount, and then that will linearize the data. So here for amount, sometimes what you'll need to do in your spreadsheet is check to see 1 divided by amount. So equals 1 divided by this. And so you'd graph all three, and whatever has the best R squared is either zero order kinetics, first order kinetics, or second order kinetics. So that's the problem solving strategy for kinetics. Okay. Right. All right. So I need to get those in-class exercises from you before you leave. Let's just look at the announcements before you go, though. Remind ourselves of a few things. If you get a chance, bring your computer to class on Sunday. Homework number 2 is due on Tuesday. My office hours are Sunday, Tuesday, and Thursday from 10 until 12. And my office is on the 3rd floor of the main building. I'd welcome to have you stop by if you've got questions. Feel free. And I'll see you in class on Sunday.